It's muted in the back somehow. Oh, no, it works.
Looks like it's all right. Okay, so we're going to get started. Today we're going to have a guest lecture from Professor Peter Abiel here at Berkeley. And Peter is going to tell us about some robotics and deep RL topics.
Okay, Sergey, thanks for the introduction and thanks for having me. Welcome, everybody. I'll talk about 3 topics today. I'll tell a little bit about adversarial attacks on neural network policies. Then I'll tell a little bit about how language, or at least multi-agent communication, can emerge from agents acting in environments where that helps them achieve goals. And then I'll tell you about an application of essentially model-based reinforcement learning to autonomous helicopter flight. In fact, a combination of imitation learning and model-based RL. So let's start with adversarial examples in RL. So the kind of questions that motivate the work we've been doing on this topic is, can we brainwash RL agents? That is, can we give them a message that they internally absorb in their, let's say, recurrent neural net internal state, but then nothing shows for a long time, and then all of a sudden maybe something triggers them to act out on what we programmed into them, and then they do something bad, like maybe kill somebody, like you would see in the movies. And so this would be a sleeper agent type of application. But before we dive into that, let's actually just remind ourselves of what adversarial examples are. So this is an original picture of a bus. This is a perturbed picture of a bus. An interesting finding in a paper by Zaghetti et al. About 3-4 years ago now, I think, is that actually a neural net trained to classify things like buses and so forth will classify the second one as an ostrich. For a human, of course, it's obvious this is a bus, but somehow for the neural net, it gets the wrong decision. Now, humans aren't totally immune to adversarial examples or weird things in images either. For example, what you see on the left is actually a mix of a type of muffin and a type of dog. But it's very hard to keep them apart. What you see here on the right is all parallel lines, but for humans, they look non-parallel. And so what this is somehow our priors and so forth are such that it's very hard for us to unsee some skewedness about these lines. So what's the technique underneath the example I showed you with the bus? Here's the idea. What we would like to do is to somehow fool the neural net, but in a way that doesn't fool a human. And so originally we'd have a bus. The machine learning algorithm says school bus. The human would also say school bus based on that picture. An adversarial perturbation will change something in the pixels. The machine learning algorithm is then supposed to say something else, for example, ostrich, and the human is still supposed to say school bus. And so the idea here is to try and perturb a minimal amount in the image under some norm, and that will ensure that the human still sees the same thing, but somehow there might exist very small perturbations that lead to the neural net making the wrong decision. So here's how you would set this up in a kind of more maybe realistic scenario. If you really want to break something, imagine you have a self-driving car. It's driving around. It's using a deep neural net to look at things like traffic signs, for example, a stop sign. But then you might put a tiny little sticker or a few stickers on the stop sign somewhere, and then the neural net will be fooled and will think that the stop sign is now a different sign, for example, a right turn only sign. So this is a real issue for deployment of neural nets in the real world, and so it's good to understand what's going on here. And what we'll look at is how this actually applies in reinforcement learning. The technique underneath is a simple optimization. So it's very, very simple. It's more surprising that this works than that the technique is complicated. You have an image. If you process it with a neural net, you'll get a classification. You want a different classification. You can backpropagate through the neural net to minimize the probability rather than maximize the probability of the correct label. Don't backpropagate to change the weights, but backpropagate to make changes in the original pixels that feed into it. Make that update, make a small update, and repeat until the probability of the wrong label becomes higher than the probability of the right label. At that point, you have your adversarial example. Here are some quantitative results. So an MNIST simple digit classification data set the adversarial success rate is 97% with just a 4% average distortion. That means very small distortions are enough to perturb almost all the digits. It's not that somebody has to pick a particular picture and say, oh my god, here this works. It works on most of them. CFAR 10, very high success rates too, and very limited distortion. So here are some examples from CFAR 10, where the top is the original, the bottom is the perturbed one, and there's just a few points that are perturbed that are enough to fool it. For example, this frog here is turned into a bird. This horse here is turned into an automobile, and I think this is a, well, I'm not sure what this is. Very hard data set, CFAR 10 for humans sometimes. The dog is turned into a bird. OK, so how about RL? Can we do the same thing there? So what's the setup? Typically in RL, we'd have some state or observation, XT or OT, goes into a policy, assume the policy has been trained, and an action AT comes out. The white box adversarial setting would be one where the adversarial player sitting here has access to the policy pi theta. That's what this means. So when the input XT comes in, adversary looks at pi theta, what pi theta would do, looks at what perturbation would throw off pi theta as the perturbation. At that point, it gets fed into pi theta, and now the wrong action might come out. In the black box case, instead of having access to pi theta, the adversary just has access to some other policy pi theta prime. So this is often the most realistic scenario because you might not be able to access the code of the policy that is being used, at least not very directly. And so you might have a proxy of that. Maybe do something like running behavioral cloning, or you train your own policy for the same task. That's what we'll do in our work here. You train your own policy for the same task, and based on your own policy trained on the same task, you compute perturbations. And then the question is, would those perturbations still be effective on the policy that the actual player is running? OK, so the way we did it in our work is we did something even simpler than the iterative procedure I showed to you. We used something called fast gradient sine method, which when you backpropagate, you effectively look at a linearization of the neural net. You can just assume that that linearization is valid and just essentially do only one update. Backpropagate once, look at the gradient direction of outcomes that the neural net makes as decision with respect to input pixels, and just take a step that's of a certain size in the direction that maximally perturbs what the action would be, without iterating and taking new gradients. And even that turns out to be very effective, which is very surprising. OK, so you can then put different norm constraints on this. You can say, I want adversarial perturbation where the infinity norm is small. That means that the maximum amount of perturbation for any given pixel is small. L2 norm means things are on average about the same everywhere. How much you perturb is the typical outcome. Or 1 norm, which means that you will perturb as few pixels as possible. But you can perturb each pixel a little more because you get the same budget as you get in the other ones. OK, so let's look at an example. Here's the game of Pong, one of the standard Atari games. On the left is the original frame, and the ball is moving towards the paddle of the player on the right. Then if you run adversarial perturbation mechanism, what you get out is that you want to perturb over here. Makes a lot of sense because that's placing the ball much lower than it's actually going to be. This is the perturbed image, and it turns out that it's sufficiently perturbed in this case that the paddle would move down, and so the player would lose the point in this particular setting. You can also do other perturbations. This is if you use the infinity norm. This is what the perturbation pattern looks like. This is a scaled up version of the perturbation pattern. So when you actually apply it, it's very hard to notice what's here because this is multiplied with epsilon to apply it over here. But just as well here, this kind of perturbation, less visible because it's distributed everywhere, will fool the player and make it miss the ball. You can analyze this a little more quantitatively. So what we looked at here is how quickly does performance of an algorithm decay as a function of the amount of perturbation. So the horizontal axis in every scenario here is the norm of the perturbation that you're allowed to make to the image. The vertical axis is the performance. So if the norm of perturbation is 0, you're in the original setting, and that's all the way on the left on each graph. And so you'd see how well did the policy play without any adversaries present. Then we looked at 4 different games, and we looked at 3 different algorithms. So top one, A3C, TRPO, DQN. You covered all of those in this class. And so you can now see that all 3 of these are susceptible to adversarial perturbations. Now, this is the white box case, where we assume we have access to the policy, can backpropagate through it, and then perturb based on that. We can also see that depending on the norm, things decay more quickly. So the infinity norm, things stay good for a little longer, whereas with the one norm, where you have more local budget in some sense, where you can focus your effort more on a small number of pixels rather than having to distribute it over all of them more evenly, then it's actually a lot quicker, that's the blue curves, to perturb what's happening. How about the black box case? So 3 columns, 3 different norms, 3 rows are 3 different algorithms. And so what we did here is we trained the actual player with A3C for the top row, did a different training session, but also A3C for the adversary, then computed the perturbations for the adversary's network, applied them to the actual player, and we see again that this actually is quite effective. You can go a step further, actually. Actually, let me show you some videos first. So what you see here is chopper command. On the left, you'll see the original game, where there's no adversary present. Here, you'll see the raw input, but while the adversary is present. So the way the game will play out here when you watch this video will be different than over here, because the adversary will perturb the actions taken by the player, hence the game will play out differently. This is the adversarial perturbation, scaled up to make it visible what it is. And then here is what it looks like for the player, what it executes on in terms of pixels. All right, so what is this game? You're flying a helicopter, and you are shooting things that come at you. And actually, you have a tiny little map at the bottom here that shows you what's coming up ahead of you. So what we want to see is the difference between this and this, or the one in the back, and see if this one is indeed better, so that this one is really suffering from the perturbations. Score-wise, this one's still below 1,000. This one's above almost 3,000 now. This one has died a few more times. If you look at the perturbations where they're happening, they're all happening over here almost. This is L1 norm, so it's actually putting the perturbations all inside the map that gives you the look ahead, which is really interesting that it says, okay, most effective way to destroy the capabilities of this player is destroy their ability to look ahead in the game. This one's still going on, or was still going on, much longer than the one with the adversary. There's some related work that's been happening. So for example, Bezdan and Munir, what they looked at is how can you prevent the policy from learning how to optimize true reward? So the idea here is that you come in at training time. While the policy is being trained, you perturb the images, and you hope that the result is that this policy cannot be trained up that way. And in fact, they show that this is possible. In this case, they do it for DQN. Some work by Don Song's group here at Berkeley. What they looked at is minimize the number of perturbations you insert and still have an effect. What I mean with minimize is minimize over time. So rather than at every time slice getting a chance to perturb, you try to minimize how often you insert, and maybe that's an interesting thing to do, because now somebody's watching the agent play, and if they don't watch all the time, but just take a glimpse every now and then, they might not see anything that's wrong with the images that are being fed into the agent, yet somehow the agent is failing. And they also looked at some defenses where you retrain, as you have an adversary, you retrain against what happens in the presence of the adversary, and you can see if you train in the presence of the adversary, you can crank up performance again to be more robust against that. The work by Lin et al. Looks at injecting fewer perturbations, much like the work in Don Song's group. What they looked at specifically, rather than just minimizing how often they do it, to use a guidance for that, in Don's group, they looked at the value of the state. In this work, they looked at the difference between the Q values. So if there is a Q value for an action that is very high, if another action very low, then it means that if you perturb, the expected reward can be highly changed. And so that's where they insert the perturbations, though from the previous work, it also seems like just doing it whenever the values are high is already a pretty good proxy for something like this. Then the other thing they looked at is how you can lead an agent to a goal state. So what you would do there is you would train a video prediction model. You would then, based on the action conditional video prediction model, you would find out for the current situation, what is the sequence of actions that would lead to a state that you might want to get the system into. And then you do adversarial perturbations that favor that sequence of actions. And that way you can guide an agent with minimal perturbation to wherever you want the agent to go. I mean, not always, but it's surprisingly effective. Actually, one slide I forgot to show that I want to mention also is that the black box version that we investigated also works if your adversary doesn't know which reinforcement learning algorithm you're using. So you can train your adversary with A3C, DQN, or TRPO. Those are the three we tested. And whatever you find based on the policy trained with any of those three algorithms will be effective against any of the other three algorithms to perturb what the agent is able to do. Some current directions we're looking at, and I think quite a few other people are probably looking at it too. The original motivation, how can we get these kind of dormant examples where we perturb an agent early in time, but everything looks normal, and then much later in time, all of a sudden something goes wrong. You can imagine, you tell an agent, please fetch a cup of water for me, but the agent is busy for a whole, you say, fetch a cup of water for me for 11 o'clock, and the agent is busy all day doing all the right things, and fetching water for a lot of people and so forth, but then when it's your turn, it actually doesn't do it, does something completely different, and there's no way to anticipate this because somehow this happened in a way where the agent was either mistrained or trained to be very receptive to weird perturbations at execution time. Some initial results, but it's still got a way to go to really have significant results there. Looking at optimizing different reward functions and how to see how this can work in an actual robot and see if a robot can maybe get some funny behaviors as a consequence of this. Any questions about this?
If you do just like periodic adversarial perturbations, will you still get the same behavior? Like, say if you're not adversarial every time step, but you only do it every so often?
So the question was, if you can only do periodic perturbations rather than every time step, what's still possible then? So it turns out that the work in Don Song's group looked at minimizing how often you perturb, but it wasn't periodic per se. It wasn't at regular intervals. The other work also looked at minimizing how often you perturb, but not at what happens if you have regular intervals. So I don't think anybody's really looked at what would happen then. It seems likely from these findings it would still be effective, but hard to say without somebody actually running the experiments. Sergey.
So with the helicopter game, it seemed like the perturbation was actually a lot more interpretable than is typical for adversarial examples. Have you guys tried to look at whether the issue is with, or I guess not issue, but with that effect is due to the fact that it's RL or due to the synthetic images?
So the question was, it seems that the perturbation is a lot easier to interpret in the helicopter example than typical adversarial examples for images. I think part of it is that it's easier for us to spot them on these very simple images to see what's happening. So it's harder to hide a perturbation, especially if you use a one-norm-based perturbation scheme where you're encouraging the system to put almost all its energy into a few pixels. I think if you did that for a regular image, it would just be a few noisy speckles, and you wouldn't notice. It's a good question then, though, if you would do it in a regular image, would it have as big an effect? Because if it's far less noticeable, then maybe it also won't have as much power as it can have in these images where a lot of the background is blank, and if you all of a sudden put something on it, then it might look like an object showed up over there. Because just seeing something bright against the darker background tells you there's an object, and usually there are adversaries to these objects, so then you'll act based on these objects. Yes? So in these plots, so the question was, to which extent does it depend on the amplitude of the perturbation? And so in these plots, the horizontal axis is the amplitude of the perturbation, and vertical axis is performance, and higher is better. So these are scores in the games. And so what you see is when there is 0 amplitude, you achieve the original score. As long as the amplitude is pretty small, you achieve roughly the original score. And then at some point, it just drops down quite quickly, actually, for most of these. And so, yes, it matters that you have sufficient amplitude, but it doesn't have to be as large as you might maybe naturally expect. Definitely does not have to be as large as it typically would have to be for humans, especially if you use the infinity norm type perturbations, which are going to spread out everywhere and almost invisible. Yes?
Have you thought about vulnerability metrics to apply or
So what do you mean with that?
based upon different algorithms or different domains, can you kind of quantify some kind of vulnerability in some metric form?
So the question is, based on this, can we quantify the vulnerability of different policies? You can imagine maybe similar to robust control theory, where you would say this controller, at least that's something that comes to my mind, where you could say this controller can withstand a certain amount of random or adversarial perturbation and still be stable. That's a good question. I don't think anybody has explicitly quantified a property like that. The kind of thing people have been trying to do is see if they can come up with a scheme that is less vulnerable. So they'll train in a different way and then see if the norm that is required to have adversarial examples might go up because you maybe train something up in a more robust way. But I haven't seen anybody have very explicit robustness measures or avoidance of vulnerability measures for these. All right, let's switch to the second topic for today's lecture, the emergence of grounded compositional language in multi-agent populations. This is joint work with Igor Mordac, who's a research scientist at OpenAI. So let's start with what is the current dominant paradigm in machine learning for language problems. So a typical thing would be you want to build some language system, automatic language system. You might collect a large amount of data, some supervised maybe, some unsupervised. You feed it in your network, and then maybe get something out if you have unsupervised data, something like a chatbot that has seen what people tend to say and then says, hey, a good first sentence to say is, hi, how are you doing today? And there are actually some very impressive results with all of this, training deep nets to do things like machine translation, sentiment analysis, document summarization, dialogue, and so forth. But is there something missing here? If we think about what's happening there, huge corpora are being collected, sometimes supervised, sometimes unsupervised, and something is trained to match the statistics in the language data. OK, let's give it some thought what might be missing here. Any thoughts? Could there be something that you cannot learn from just looking at the statistics of language? Because if there were something you could not learn from just looking at the statistics of language, then that would be missing here. OK, so let's think about that. The notion here is grounding. So we want more than just understand the statistics of language. We want to understand how language relates to the real world. So the idea that words and language are tied to something directly is exactly the notion of grounding. Deep learning in the static data sets will only learn statistical structure. This will typically not sufficient to carry out real tasks. Think of a very simple scenario. Let's imagine you're trying to train let's say you're trying to train Alexa to do things for you at home. And let's assume all Alexa has access to is statistics of language, things that have happened before and dialogue that has happened before. And now it's been trained, and you say, hey, Alexa, can you, well, it's Alexa. So let's say, hey Alexa, can you order a new clicker for me for my next presentation? Well, what should Alexa say? Well, the natural answer is, sure, no problem. I just ordered it on Amazon. It'll arrive in 2 days. But actually, that's the right answer, independent of what Alexa actually did in some sense. Statistically speaking, Alexa will just say that will be correct in terms of log likelihood of saying the right thing, even if nothing happens underneath. And that's not what you want. But if all you get is statistics of language, then you actually don't get anything beyond that. All you get is the right answer, but no action underneath. And so grounding is really needed to kind of work this out and somehow relate what is being said to what also happens in the real world when people say that. And then you might get agents that can do something based on dialogue rather than just have a dialogue with you. Now, how to do this? There's many ways to try to tackle this problem, and you can imagine that you would collect supervised data where you see, well, if a personal assistant answers something, what's the action they took, and then somehow tie that all together. What we've been interested in here is to see if we can actually have this emerge automatically. And so, more generally, can we have language as a whole emerge automatically by setting up environments? In the future, hopefully, it's something like a real-world environment. For now, a small domain to test the scientific questions. Can we set up environments where if agents communicate in the right way, then they can be more effective in those environments? Because if we can do that, then maybe by running reinforcement learning in those environments, these agents will decide to invent language because it's the most effective way to act in this kind of environment. And then in the long run, you might hope that if they invent a language to act in that environment, and maybe some human players act in this environment too, then the language will not be arbitrary. It'll be something like English, Chinese, and so forth. Or maybe they just learn on their own, and then later you learn a machine translation between their language and languages that you care about, and now they have a grounded understanding of language. That's the hope. Still a long way to go, actually. A lot of future research can be done here. But here are some initial results that I'll tell you about. So the scenario we're looking at is we have, in this scenario here, 3 landmarks, but this will vary from situation to situation, but there will always be landmarks and agents. The big disks are landmarks, and the big, more solidly colored disks are landmarks, and then the small ones here are the agents, and then each agent will have a bubble at times hanging off, and that's what they're saying at that time. Okay, so that's the setup. And the task would be something along the lines of, maybe blue agent has to go to red landmark, green agent has to go to green landmark, something like that. And red agent doesn't have to do anything. But instead of each agent being told what they're supposed to do, instead, the blue agent might be told what the red agent is supposed to do. The green agent might be told what the blue agent is supposed to do, and the red agent might be told what the green agent is supposed to do. But they're not being told in a language, they're just being told in terms of a simple vector that comes in that encodes the reward function. Then they're supposed to take this vector, if they do well, take this vector that encodes the reward function, turn it into symbols they emit. These symbols that they emit can be heard by all the other agents. Then imagine these other agents have a recurrent neural net, absorb those symbols, based on that decide what to do, and if somehow they manage to sync up, invent a language where, based on the reward vector that comes in, emit the right information, it gets absorbed the right way, and right here can be many things. It just needs to be something they agree on. There's many solutions, many permutations that will achieve the same thing. Then the other agent can pick up on it, do the right thing most effectively. Okay. And so the hope is that, and the thinking here is that this might be the simplest kind of environment where you can get interesting behavior. Because what can you have here? We'd like to have compositional language, not one symbol per full scenario, but we would like the agents to be encouraged to emit a sequence of symbols. So for example here, maybe if you're the blue agent and you were told something about what the red agent is supposed to do, you emit some symbol that tells the other agents which agent you're sending a message to. Then you emit something about what they're supposed to do. And what they're supposed to do consists of 2 parts. It could be, there's the action part, where to look at, or where to go to, or to do nothing. And then there is the what it is that you're supposed to look at, or what it is that you're supposed to go to, which is the 3rd word. They don't have to use it in this sequence. They can do other things. And in fact, if you give them too large a vocabulary, they'll often put it all into one symbol for each combination. But if you limit the amount they can emit at each time step, actually you'll see grounded compositional language emerge. What does it look like underneath? So the communication outputs that we use are discrete. So these agents have to output discrete symbols. They can't use continuous things. What's the full setup? There is coordinates for each agent. There is also coordinates for each landmark. There is, in this case, this is the communication. That is, every agent has, there's capital N agents. Each agent has communicated at the current time, t-1. And then the last part here is, I believe, what is that part? That's the memory. That's the internal memory of the agents. So each agent has internal memory, 1 through n. Then for a single agent, what happens is they take in all the information about where the other agents are in themselves relative to their own position, because they don't know absolute coordinates. They only know their own world. So the relative version of this goes into the agent. All the communication goes into the agent. And then their own memory is accessible to them. Then the agent will update its internal state, output something, and all of the agents will do that. The reward function we use here is a continuous reward function that penalizes for square distance from goals that you're supposed to achieve. And the optimization we're running here, the reinforcement learning we're running, is with backpropagation through time. So you saw this actually back in Sergey's early lectures, and then again in John's lectures a little later, that you can do reinforcement learning. If you have a dynamics model, which we assume here access to the dynamics model, then you can backpropagate through time. And actually, if you then have a reward function that's a little bit shaped like a quadratic distance from a goal, you can backpropagate the effect of the reward and see how you can change your path, change your communication to do better. The tricky part here is that there are discrete variables, namely the communication. But it turns out there's a trick called the Gumbel softmax trick, which allows you to still do backpropagation through time, even when you have discrete variables. And so that's how we got this to work. We also have run experiments where we don't do backpropagation through time. If you don't have access to a dynamics model, let's say, so far that has proven much, much harder to get to work than if you do have the dynamics models and you can backpropagate through time. So let's see. This is what an agent looks like internally. They have access to coordinates of the other agents relative to them, coordinates of all the landmarks, capital M landmarks relative to them. Full convolutional nets process this, gets pooled, and there's a feature vector based on that. Then there is what was communicated, gets processed, gets pooled. And then here is the goal vector that the agent had. It's not the goal for themselves. It's a goal that they were communicated about that's part of the full specification, but that actually applies to other agents than themselves. And then based on that, they'll take a physical action. This is all in continuous space. So they'll move in a continuous space and a communication action. OK, so let's take a look at what's possible here. So first, let's look at the environments. So this is just single agents that were trained with backpropagation through time. And you see that they can learn effectively. The single agent can learn to effectively optimize the reward. There was going to, there was look at. It's not being told. There's no language here. We're just sanity checking that backpropagation through time indeed can work for this kind of environments. Here we're describing the goals of the different agents. Actually, the small ones are the landmarks. Then here again, actually, let me skip forward to 143. Here. OK, so what are we looking at here? The green agent's goal is to get the red agent to look at red. The green agent has not sent a message yet, because it's still time 0. They haven't taken an action yet, but they've been given a goal vector. They're not giving it in natural language. They're given a reward function, partial reward function description. That is this. Blue agent is being told that the green agent should look at green, and then the blue agent should go to red, is what the red agent knows. That's the starting configuration. And so what you'll see happen is that over time, these agents will emit communication symbols. Now, they'll actually not emit English, because they don't know how to ground this in English. They have just, this is after training, they invented their own language. But what we did is we looked at the symbols they emit, look at the consistency that exists when they use which symbol, and then retroactively mapped English words onto this. So one way to look at this is that we as humans, in fact, we is really Igor, Igor looked at this and essentially built a machine translation system by hand for this simple world to do machine translation between what these agents are talking about and English. And that way we can more easily follow along with what they're saying. Otherwise, it would be very hard to understand. And what you'll see is that on the right here, you'll see a message pop up that encodes what they've been told. And on the left, you'll see the agents then start taking actions according to what they've been told. Ooh, that didn't play. Let's go back. Okay, we're back where we were. So on the right, you'll see build-up of the messages. And on the left, you'll see the agents start moving. So the first agent says red agent, look at. Okay, so the order in which they say things is not the way we would say things, but it makes sense. They first say something about the landmark that matters, then they say something about the agent that matters or the verb. But sometimes they switch it up. You can see they actually learn to perform these tasks very reliably. You can also actually mix it up. So you go around some experiments where what he did is he did not give them communication abilities. So he would just give them the ability, then instead of communicating by words, one agent is being told what the other agent is supposed to do, and only the other agent has an objective. And now the first agent will actually physically move to the target location, and the other agent will learn that the right thing to do is to follow this first agent. So there's the nonverbal communication. And so that's it. In this case, pointing is allowed, and so the agent is allowed to point, and the other agent is picking up on that, and then is able to do the right thing. You can do, if you can't point, you can actually move where the other agent is supposed to move. It'll learn to follow that. And if the other agent is blind and can't watch you point or can't watch you go anywhere, then if you give the agents the ability to have physical interaction, then the agent that knows what the goal is actually will go push the other agent to the target location. It's not that easy to push a sphere with a sphere, but it is getting it there. All right. Any questions about this part? Yes, Aldo.
Have you tried with like real robots or something? Like some sort of body?
It's a good question. How about doing this with real robots? We haven't tried that yet. So in terms of future directions we're looking at is things like, can we get this to work without needing backpropagation through time? And the reason that's interesting to get it to work without needing full backpropagation through time is that relying on backpropagation through time relies on a few things. It relies on, I mean, it's nice if you can set up a good simulated environment and it's very effective. So in that sense, it's good. But if you want maybe some more distributed training or you want humans in the loop, you will not have a perfect model. You can't backpropagate through the humans model. And so you'll have to do something else there. If you're in a complicated world where maybe the agents have to do complicated tasks and model-free RL algorithms might, for some reason, be more effective for some of these tasks than model-based algorithms, then you can't really rely on the backpropagation through time. So that's one of the kind of, it's nice, it works as a great proof of concept, and I think you can go very far, but research-wise, to ensure that we get full coverage, getting it to work in a model-free way also for the scenarios where that's important is actually what we've been pushing more than getting it onto a physical robot. Garrett.
So you said that when agents communicate, they broadcast symbols to all the other agents. Have you looked at situations where they have to communicate one-on-one to each other?
Good question. Not yet. Maybe you should try it. Not that you don't have enough to try yet as is, but okay, let's take a 2-minute break here, and then after the break, let's look at the third topic for today's lecture. Mm-hmm.
Did you guys try anything that involved like somehow adding noise to the communication channel?
So let's see. Might Igor have tried it? Maybe. Am I aware of it?
Okay.
No, I don't think so.
It seems like when it comes to sort of plausible communication protocols, resilience to noise might end up being a pretty big factor for getting the right kind of structures to emerge.
Yes, especially it could be a factor that makes it why language is discrete as opposed to putting noise on the channel could have that emerge directly rather than having to impose discrete symbols.
Did you guys try just giving it fake symbols after you figure out what protocol it converged on? To see if you can get it to do things?
To see if we can get it to do
Yeah.
things?
Well, because right now in all those demos, the actual...
Agents are still communicating, yeah. It's
Yeah.
not a human commanding the agent.
There's never any intervention about which communications are carried out.
Yeah, it'd be fun to try. I think, to say the least, it'd make for a fun live demo to type in some commands to the agents and see if they follow them or not. Especially if they're imperfect and only follow them 95% of the time.
Well, and they might have certain idiosyncrasies. I mean, say, okay, well, since I'm used to seeing exactly one command per episode, I'll like follow the command, and then if the second one arrives, something terrible happens.
That's possible.
There's
yeah.
a communication protocol, but there's also the policy that actually reacts to it, and that policy might itself make a lot of assumptions on the structure of the
Yeah.
communication channel.
So right now, the communication channel, you pay an energy cost for communicating. So that's why they stopped communicating after they emitted their 3 symbols. So it'll be interesting to see. I like this idea of things like, what if you want them to change their mind, like you change your mind about what an agent is supposed to do, that would be the non-adversarial version, and see if they're able to listen to that.
They get frustrated, just give up. just like real people do, like change their mind a lot.
This person, I'm just going. Well, the typical thing you see when no learning happens is that they move to the middle of all landmarks. So when the learning is not effective, because that's where you kind of, on average, get something, but nothing great, because it's a squared error type thing. That is the version of giving up and going nowhere. And for the not end-to-end differentiable version, that's often what emerges. They can't figure out what to do. I mean, I think in the next half year here, it will be figured out how to do the non-differentiable version, but for now, it doesn't fully get there. Yeah. Let's see, maybe I should restart. All right, let's restart. Any questions about the first half that we went through? All right, let's switch to our third topic then. We actually have a one-slide fourth topic later too. So autonomous helicopter flight. It's a problem I worked on during my PhD back at Stanford. I was working with Professor Andrew Ng at the time, and kind of the reason he got into helicopter flight actually as a PhD student at Berkeley is that he had done a lot of work in, made many contributions to machine learning, among them some significant contributions in reinforcement learning. And people challenged him and said, look, if you want to show that this is effective, this reinforcement learning thing that a lot of people, definitely at the time, still thought of as something that only works for toy examples. So to show that that's not the case, you should pick a very challenging control problem, a problem that most people think of as, at the time, the most challenging control problem, namely helicopter flight. and get it to work on that. If you get it to work on that, then people will take your reinforcement learning stories a lot more seriously. And so that's what he decided to take on at the end of his PhD here, and then also during his initial years at Stanford when I was a PhD student with him. So why is helicopter control difficult? First of all, helicopter dynamics are unstable. What does that mean? It means that if you don't carefully pay attention to the helicopter and adjust your controls based on what's happening with the helicopter, it'll drop out of the sky. Probably the most accurate way to think of helicopter control in terms of, if you're not familiar with helicopter dynamics, is think of a, let's say, a glass plate that you're holding. You have a marble on top of that, and there is some wind and so forth, so this glass plate actually oscillates a little bit, and the helicopter oscillates too, so there's some oscillation based on that. So this marble has some built-in oscillation, and you're holding this plate, it's oscillating, the marble's oscillating, and actually, while you're doing this, you're trying to keep this marble in place. That's going to be a hard problem, because naturally it's going to want to roll off the plate. If you don't pay attention for just a fraction of a second, it's gone. Same thing with a helicopter. In fact, it's extremely similar, because the way you move a helicopter, let's say, forward is by tilting the nose down, because you only have vertical thrust. You don't have forward thrust or sideways thrust. Same with the glass plate and the marble. You actually have to tilt the nose of the glass plate down, and then you can move forward. And then the combination of assuming you can only apply a vertical thrust to the glass plate, of course you do a little more there, you actually get the same setup as your helicopter. Now, unstable systems don't need to be hard to control. It just means that you have to pay a lot of attention to them, because otherwise they'll run away from you. But if, let's say, you had just a simple linear system, but it happens to be unstable, but it's a simple linear dynamical system, and you have reasonably high control bandwidth, then you can just run something like LQR, find a feedback controller that stabilizes it, and there you are. You have stabilized your linear system. But helicopter has nonlinear dynamics, which makes it harder, and in fact, very complicated nonlinear dynamics. And the reason the dynamics are complicated is largely the airflow. Airflow is very difficult to model. Fluid dynamics is also very expensive to simulate. It's not practical with any of the current systems to actually fully simulate the airflow around the helicopter in a reasonable way in real time, because that really would be the full state of your system. It would not just be the helicopter, it would also be what all the air is doing around your helicopter. That means solving partial differential equations real time, and that even assumes that you can measure the initial state to actually get a feel for what this system starts from and simulate. So very difficult to handle that. Then there is mechanical coupling between different parts of the helicopter, and there's the blade dynamics. So the blades go around in a circle, but they actually also flap up and down. They might lead and lag a little bit as they experience air resistance. So it's quite complicated what these blades do. The consequence, and aside from that, is that you also get only noisy estimates of position, orientation, velocity, and angular rate. So if you've ever run control experiments on a robot, and you think about, well, let's introduce some noise into the system and see what happens. And the natural thing you probably did is you introduce some noise into the system where you said, oh, I apply a control, and then I add some noise to the control, and that way my control becomes harder. That does become harder. It becomes even way harder if you actually don't give your controller access to the true state, but start perturbing the observation of the state. Because now you're controlling based on something that might not be that precise, and so when you're thinking you should go forward, maybe you should be going backward. That's a much harder thing to deal with than applying a control, and it's not exactly applied the way you asked for. And so all of this combined makes it a very hard control problem to control a helicopter. Despite it being such a hard problem, in the early 2000s, people started making a lot of progress on this, including Andrew Ng's reinforcement learning-based approach in 2001, and then 2004, next work, and then a lot more work later. And if you look at what happened here, actually a variety of techniques was applied. So it's not that one technique was the winner. A lot of different techniques were able to do hover with a helicopter. Inner-outer loop PID control. That means that you have a notion of, well, I can only move my helicopter translationally by rotating it. So I'm going to have an inner-outer loop where the inner loop is about orientation and the outer loop is about translation of the helicopter. And then the outer loop can ask something from the inner loop. That's a hierarchical controller, a very nice hierarchical control scheme that works beautifully for helicopters. You can then tune the gains in there yourself or do it automatically. This should be an infinity, actually. It's infinity control, which is a robust control method, LQR, and so forth. All of these methods worked. And in fact, they worked quite surprisingly well, despite it generally being considered a very hard control problem. So what we're watching here is fully autonomous, in fact, inverted hover of, in this case, the Stanford helicopter entering this project. So what you see here is that actually a helicopter is stabilized upside down. How does this even work? For that, you got to think about how the helicopter aerodynamically works. So the way a helicopter works is that you have blades that spin around. You control the helicopter's vertical thrust, not by changing the engine speed, but by actually changing the angle of attack of the blades. So you tilt them up more, you'll push more air down, and that way you'll thrust more. And actually, you can choose a negative angle of attack in case you want to go down very quickly, or if you're upside down, you can then sustain your flight inverted. In fact, it's even more efficient to fly this way. Any thoughts why it'd be more efficient to fly upside down?
The downward flowing air doesn't have to pass over the fuselage of the vehicle.
So Sergey has a suggestion, which is the correct suggestion. You generate a downward airflow here. And the way the aerodynamics works out approximately is that you have an intake velocity of the air, which is some velocity v. And on the other side of the blades, it's 2v, so twice the speed. Drag is proportional to quadratic the speed, so you have 4 times more drag that would be happening below the blades than above the blades. And so you have, this way, you have 4 times less downward drag on the helicopter than if you were to fly the normal way. Of course, there are many reasons people in practice don't fly this way. It's more complicated you need some system for people to be happy with this kind of flight. But also aerodynamically, it's nice if you can design your blades and structurally to know that they're always going to be used in one direction rather than sometimes one way, sometimes the other way. Because for full-size helicopters, the blades are not symmetrically designed. They're asymmetrically designed to be more aerodynamically efficient. But these are stunt helicopters for RC flight, and people want to do crazy things with them, and so they build them this way. What are your other controls that you have for a helicopter? You actually have 4 total control channels. The first one is the angle of attack of the main rotor blade. Then the main rotor will generate there will be a counter torque on the body of the helicopter that will make the body of the helicopter spin in the opposite direction of the main blades. Now, that's what the tail rotor is largely for, to counter that torque. Tail rotor also helps you with choosing which direction you're facing, but largely the thrust exerted by the tail rotor compensates for the counter torque you're getting. Tail rotor also has a change in angle of attack to adjust how much it's thrusting. Now, the reason people would do it is based on angle of attack rather than changing speed is that it's faster to change the angle of attack, especially once you have a lot of inertia in your blades, than it is to change the speed of the blades. 2 more controls. So what I've told you so far could in principle have you go up, down, and could have you look in the direction you want to look, but you can't yet move anywhere, or if the wind pushes you somewhere, you're going at will of the wind. You have controls to tilt the nose down and roll sideways. And the way you do that is by changing the angle of attack of the blades differentially, front, back, left, right. And by changing that differentially, I mean, you don't with your joystick have to change it in sync with the blades. There's a swash plate mechanism on the helicopter that you choose an average difference between left, right, front, back with your joystick, and then the swash plate will execute that for you at 30 revolutions per second. So you definitely couldn't keep up if you had to sync it yourself. So then if you want to fly forward, you apply a torque corresponding to bringing the nose down. Once your nose is down, your vertical thrust in the frame of the helicopter is partially forward in the earth-fixed frame and partially still vertical to keep you up in the air. If you think about the actual physics of what's happening when you try to rotate, when you apply a differential thrust left, right, or front, back with the main rotor blades, what happens is the main rotor blades will actually start moving. Then there's a little bar that connects the rotor to the helicopter. That bar will have some elastic force and will then pull the helicopter to follow along with the blade. And in fact, those are some, if you look at detailed data, you'll see actually oscillations of the helicopter relative to the blades at a pretty high frequency that you need to take care of. Now, that was beautiful. The helicopter was flying upside down. It seems like should be quite hard to do. Maybe it's not that much harder than flying straight up. It's a little more unstable, the dynamics, because obviously the mass is now on top. But it's still, in some sense, you're solving the same problem. Just as people had looked at before, because you're always staying in the same flight regime at all times, you can approximate the helicopter with a linear dynamical system, design a linear system-based control system, let's say LQR controller. Yes, in practice, you'll have to tune it a little bit with the cost of the LQR controller because your model won't be perfect and penalize a little more, a little less for control costs, maybe changing control costs, and so forth. But if you do that for a bit, then you'll find a good control cost, find a good linear feedback controller, this will work. But then we were students at the time. We started watching some videos. This is Alan Szabo, considered one of the top 3 pilots in the world. And watching his videos felt a little different from what we had done with our own work at Stanford. So what you see here is human control. Wide range of maneuvers. That was a backwards traveling sideways tick-tock. You can see that Alan is able to control this helicopter in a very snappy way, doing very aggressive maneuvers, really pushing the limits of anything that's possible physically with this helicopter, which is far more advanced, at least I think everybody would agree with, than hovering in place or hovering in place inverted. So the question is, can we do something like this but autonomous? So we set out to do that. We did kind of the maybe standard thing you would try to do. And so what did we do? We had an expert pilot, maybe not Alan Szabo, but I would say top 10 in California rather than top 3 in the world, so still amazingly good. This pilot would collect data for us, flying all kinds of maneuvers. We would train a dynamics model based on that data. We would then choose a target trajectory. We'd say, well, we want, let's say, a roll. A roll means the helicopter is flipping around, so we design a cost function related to flipping around. We also know that you got to pause on the, after you've done 180 to do inverted thrust for a moment and then do the next 180. And so we kind of designed all things around that. We listened to him, what he thought mattered to do flips and rolls. And we said, OK, now we have a good target trajectory. We have a cost function for how much we care about following each component in the target trajectory. We run iterative LQR to find a sequence of linear feedback controllers around that target trajectory, and then let's execute it. So this is what it looks like. So hover, beginning of a trajectory, pretty good. Actually, it's flipping. So it's quite a success, actually. I don't think anybody had flipped the helicopter autonomously before. But then it pushed the controls a little too much, and helicopter went behind the trees. So what happened here? Physically, what happened is that the controller pushed the controls too hard. As a consequence, the engine could not keep pushing the blades around. There was too much air resistance, and the engine just died. The moment the engine died, you lose control over your helicopter to some extent, not fully. In fact, our helicopter pilot took back control and actually managed to spin up the blades while the engine's not running. While the helicopter goes behind the trees, managed to flip it over somehow and still landed on its legs. We didn't capture in the video. It landed too hard to fully survive, but actually it was pretty amazing how our pilot was able to, without even seeing the helicopter, without engine on, still land that thing on its feet. But definitely the autonomous controller completely failed. Push the controls too hard. Why would that happen? The reason that happens is because the controller was designed based on a simulator. The simulator resulted in a sequence of linear controllers that are pretty good in the simulator, but the real dynamics doesn't match up. So it starts deviating from the trajectory. Then, after it deviates a bit, the dynamics starts deviating even more from what the simulator had. The linear controller is even more wrong, and this keeps going on and on. You destabilize, it goes out of control. You could run model predictive control instead. You would still have the same issues here. Because the issue is not that we're using linear controllers per se. The issue is that we have a dynamics model that's not sufficiently matched with the real world. And as a consequence, dynamics model-based calculation of what the control should be is not going to work here, at least not with that kind of model. OK. So at this point, what we have at this point in time we have is hover and stationary flight regimes work well. Because you can build a really good model. If you're in a stationary flight regime, you only need to build one model and you're good to go. And that's quite feasible. And you can collect data around that regime and so forth. Now, so that's essentially build a model, then use a model-based controller, successful autonomous flight for stationary regimes. Aggressive flight maneuvers have additional challenges. First of all, you need to even know what this is that you're trying to achieve. Maybe we didn't even design the right target trajectory, and that's why it didn't work. It was trying to follow something that's not flyable. Flyable in simulation, not flyable in the real world. And then you need to have a good dynamics model. Turns out that at the time we were working on this, there was another group working on related things, Eric Frohn's group at MIT, and they managed to get their helicopter to do 3 maneuvers: a split S, a snap axial roll, and a stall turn. Stall turn is where you are flying forward, or it doesn't need to be forward, but typically you're flying forward at high speed. You want to change direction. You don't want to brake, burn all your energy to friction, and then turn around and get up to speed again. You just decide to climb to slow down, turn your kinetic energy into potential energy, and then turn it 180 at the top and come back down at the same speed. So these are pretty cool maneuvers. If we looked at what they did, expert engineering went into this of controllers that can somehow mimic human pilot demonstrations. Now, ideally, what we'd like to do, of course, is to not have to have aerodynamics, aerospace engineer experts to look at human controllers, analyze everything they're doing, and to design carefully designed controllers around that. The other thing that was happening at the time is some people were saying, look, are these maneuvers really that hard? Split S, snap axial roll, stall turn, they're really cool to watch, but are they difficult to execute or not? And kind of the question really was, if you execute a maneuver that only takes, let's say, 0.5 seconds to execute, and you have a really good controller to catch your helicopter after that maneuver, how good does that maneuver need to be? How good does your control need to be? Well, might you be able to do maybe something that's close to open loop? I mean, they were using feedback controls, but maybe you could do something in open loop that just jostles the control for 0.5 seconds. You see what happens. Hopefully it looks like what you want, and then a really good stabilizing controller catches the helicopter, let's say, in forward flight. And so we wanted to test that. So we had been working actually for 2 years at this time on trying to get this helicopter to fly reliably, loops, flips, rolls, and so forth. You saw the crash that was kind of getting somewhere, but not really getting there. And then we went out and we brought essentially nothing in terms of equipment, except for simple laptop, a recording box for the pilot's controls, and a way to then replay those controls on the helicopter. No feedback control, nothing. Okay, so after Alan Szabo's video, we called it, after Alan Szabo's video, Sunday at the Lake, we called it Sunday in Open Loop. And so let's take a look at what you can do in open loop control with a helicopter. Forward flight roll, okay? One of the maneuvers they did in MIT work. Okay, helicopter. This is just a replay of the pilot's controls. No feedback, there's no sensing on the helicopter, nothing. This is a helicopter we never flew before with our computer. We're just replaying the pilot's controls. Split S, so it's where you do a half roll followed by a half loop, another way to change direction without burning energy to friction. Wow, looks like a split S to me. Stall turn. Talked about that maneuver, so you climb up, flip the tail around. Tail flipped a little too far, so I mean, it's not a pretty stall turn, but it's a stall turn. It comes out looking pretty. So all the maneuvers they did in their paper, check mark, done. In like 5 minutes of being outside on a Sunday. Okay? Then we picked a few others. Loop. Well, happens to work too. Now a lot of this has to do with the fact that in forward flight, helicopters behave pretty well compared to other things. Takeoff, can that work too? This is completely autonomous, but just replaying a recorded sequence of controls from our pilot. It is close to the ground, so a little more worried. There it is, and it's hovering somewhere there. Inverted takeoff. We figured might as well flip the helicopter over, see what happens.
Autonomous.
Goes up, inverts. There it is. Inverted helicopter flight. Just recording some controls from our pilot. I mean, it wouldn't stay in the air for as long as you could with a stabilizing controller, but it looks like it's succeeding.
Ready. Okay.
hover. So if you do this for a while, it clearly drifts away. It doesn't actually stay in place, but it's not like it just does something crazy. Tick-tock, one of the hardest maneuvers. Supposed to go like a clock here, old school clock. Looks like a tick-tock. It's descending very quickly, so pilot had to catch controls here to save the helicopter, but it's actually looking somewhat like the motion that we want, just not precise. Chaos, the hardest maneuver. It's where you flip and roll at the same time, as well as you also spin the tail around. It actually looks like a chaos. You're supposed to stay in place when you do this as an expert pilot, not drift all over the place. But kind of what we're seeing is that for all of these maneuvers, the overall gist of the maneuver is there. It's just very imprecise, and it's definitely for the more aggressive ones going to crash within a second or two. But at least the gist is there, and it actually looks better than the flips that we did with the carefully designed controller that was climbing like crazy. Here is the forward flight double axial roll. Works too. Continuous flips. Let's see what happens there. It's flipping. Much better than the flips I showed you before, all in open loop. I mean, it's still going to go down here, and if the pilot isn't there to take back control, it would be crashing. But it works more nicely than it did before. So this interesting lesson here is that open loop can actually work surprisingly well. If you do some experiments, maybe first thing you should do with a robot is just to see what happens if you replay things in open loop and get a feel for how much feedback control is really required for your task. Still, it didn't work. You need much better control to actually do this properly, but it's surprisingly good. So what we wanted to do is see if we can learn controls from a human pilot, because clearly there's a lot of information in these demonstrations, improve it with RL, because that's going to be the way to fine-tune a controller, and then hopefully succeed at a wide range of aggressive maneuvers in rapid succession. So I think that's where a big difference is. If you do these maneuvers one at a time and then catch it in a feed-forward flight controller, well, you only need to have a good feed-forward flight controller to stabilize it. If you do them all rapidly behind each other, like Alan Jabo did, during every maneuver, you need to have stabilization happening. During your flips, during your tick-tocks, during your chaos, you need to stabilize. Otherwise, you can't do a 2-minute sequence of all of these sequenced together. So let's take a quick look at how we did this. What's difficult about specifying the target trajectory is that helicopter dynamics is complicated. If you don't specify it right, then you can't fly it. So you need to somehow get a good target trajectory. Solution, collect demonstrations from an expert. So here are the expert demonstrations. We collected many demonstrations on the real helicopter. We tracked the real helicopter. We visualize here what happened when the expert demonstrated. It's not always the same path. You could say, you could use just one, try to fly it. We did that, but the expert isn't perfect at all times. And also, actually, the sensing isn't great at all times. And so by having just one track trajectory, you will get something pretty noisy just because of bad sensing and imperfect expert demonstrations. What we'd like to do is to take these many demonstrations and turn them into a target trajectory that's better than any one of them. One way to do this is to run inference. So you could set up a graphical model, much like a hidden Markov model, but in continuous state space. If you had 2 demonstrations, you could say, OK, now these are noisy observations of the actual demonstration I wanted. And let me run inference in this model. Of course, they will not be equal in length. So you got to do something to fix that part. So what you can do is you can initialize this with one of them. Then you can run dynamic time warping, speech recognition, and biological sequence alignment technique that can optimally align sequences with dynamic programming, so very efficient. After you do that, now you have alignment. Now you can run inference to fill in what the denoise state would be. You can do that with an extended Kalman filter or smoother in this case. After you've done that, you can rerun the alignment and iterate this till this thing reaches a fixed point. And then here is what you get. The white helicopter is the denoised version. And now all these are time-aligned also the way they're displayed. So the white helicopter is the one we'll want to follow in the real world. Note that when we're denoising these, you can actually build a dynamics model into all of this. There's a dynamics model living inside a Kalman filter. So it's trying to satisfy the dynamics of the helicopter as it's doing time alignment and finding the denoise trajectory. Here's what it looks like if you have 3 double loops. You denoise it, you get this nice double loop target trajectory. Learning dynamics model. The main observation here that I think made it all work is that for the longest time, we were trying to build really good dynamics models, and it wasn't good enough. That's why the initial video had that huge failure. The dynamics models, that's the real key part, weren't good enough. You do model-based control, it's not going to work if your dynamics model is bad. How bad are these models? So we use the same technique as we used in that initial video to build dynamics models, which is building a simple nonlinear dynamics model that includes a lot of prior knowledge about how helicopters work. This is error in prediction of how much the helicopter will accelerate at a certain time. 0 is here. Ideally, this would be all 0. That means we have a perfect model during this run here. Actually, it's pretty much never 0. Minus 10 meters per second squared, that's the acceleration you get from gravity. So we're off by the same force as gravity has, up to actually 3 times gravity, how much the dynamics model is wrong in predicting what's going to happen. So you can now understand why it went so wrong in that first video. If you can't anticipate that gravity is 3 times, 4 times, in fact, because gravity is there and then there's 3 times extra on top of it, you can't predict that, then you're not going to do the right thing with your model-based controller. So how do pilots do this? How can they deal with this complicated dynamics? Well, it turns out while it's very complicated, it's actually very consistent. If the pilot flies the same sequence of maneuvers, you get a similar pattern. These are not time-aligned yet, but once you time-align, you actually see that these are consistent deviations from the dynamics model that we were learning. So what that means is that in principle, we could actually anticipate what's going to happen and use that anticipation to do better. So effectively what's going on is there's airflow that we don't have measurements of. And so when we learn the dynamics model, it's really hard to account for that. But all that stuff is going to be consistent in every execution. And we're just going to learn a time-varying model where when we learn a model at a certain time, we weight the data around that time in the time warp trajectories to learn the model at that time. And then you can reduce this error to not 0, but something much smaller than 1g, which is good enough to make this work. So let's take a look at how this all works. Our helicopter has some sensing on board, gyroscopes, accelerometers, magnetometer. This gives you effectively a noisy version of orientation, as well as angular rates. Then this goes into an extended Kalman filter together with cameras that we're looking at the helicopter. So it's like a home-built Vicon system where you have cameras look up at the helicopter. Then this goes into, after some computation, we use receding horizon differential dynamic programming. I think you covered that in the 3rd or 4th lecture here. The receding horizon part means that in this case, we plan for 20 time steps into the future. You execute just the first of the 20 time steps controls, and then replan, so the model-predictive control approach. Key is to top it off with a value function at the end, such that, because just looking 2 seconds in, well, 20 ticks is actually, let's see, we look 40 ticks ahead, 2 seconds. So looking 2 seconds ahead is not enough to do good control. You need to look further ahead. We can offline from your iterative LQR differential dynamic programming runs, get quadratic value functions. You can use those as the end cost on your 2 second look ahead to actually do the right thing in terms of anticipating the future. Once you do that and you set up a computer and so forth and the code that this runs super fast and doesn't get interrupted by any operating system calls and things like that, then you can actually get this to work at 20 hertz, including the Kalman filter at 100 hertz, control at 20 hertz. Control at 20 hertz also means that you actually don't use the full 1/20th of a second to do control. You use about half of that, 1/40th of a second, because latency is also bad. It's not great to compute an optimal control, but 1/20th of a second later only. You want to be quick based on the current state estimate to get out what you think is the right thing to do. Okay, so this is what it looks like as a whole. You collect some data, then the pilot demonstrates the air show, you learn a target trajectory, you learn a dynamics model, find optimal control policy, you fly this. Actually, typically, if you do something long, it won't fly the whole thing, but it'll fly for maybe 30 seconds into it. You collect the data, you improve your dynamics model, and this autonomous data is actually better to work off because it's automatically time-aligned. It's much easier to build a dynamics model from than the pilot data. You improve the model, go again, and repeat this, and typically in about 20 iterations of this, you get to something where the helicopter can reliably fly very precisely the maneuvers that the pilot demonstrated. So this takes about an hour in real time to train something new. And here are the results. Fully autonomous, inverted takeoff, hover. Then we wanted to check off all the maneuvers the MIT group did to make sure that we're indeed doing something beyond what they did. So we do the split S, snap roll, stall turn. That was done right there in rapid sequence though, not with catching it with feed-forward control, feed-forward flight in between. Loop, if you do a loop and you want to show you're in control, you appear with the tail around at the top. Another stall turn. You can come out tail first from these stall turns. It requires, it's less stable, so you need to be more precise with your control, but you can do that. Hurricane is fast backward flying circles. Then some more inverted flight. Knife edge fall. Fall on the side of the helicopter so it doesn't have any control. Stationary rolls and flips. These are actually some of the hardest parts of this air show because it needs to maneuver in the airflow it just generated. And what's really hard about helicopter flight is the complication of the airflow, and here you're dealing with in a very complicated way. Tick-tock, one of the hardest maneuvers according to many, and then inverted hover at the end. If you're wondering, was it flying what it was supposed to fly? Yes. White helicopter is target, black helicopter is what it flew. This is actually very precise for flying these helicopters. We compare with other groups who had helicopter flight control going on, even doing things just hover, so to say. Not that hover is easy, but it's easier than these things, and their precision would not be better than what we have throughout the entire air show on things like hover. All right. I mentioned to you can land with the engine off. Let me show that video. What you see here is engine off landings. It's called auto rotation. What you do is you bleed. You have energy because you're high up. You have the engine off, so the blades will not be automatically propelled. You can control the helicopter to capture that potential energy into kinetic energy of the blades rather than kinetic energy of the body of the helicopter going down. When you have the kinetic energy in the blades, then once you're close to the ground, you can change the angle of attack of the blades, generate a strong downward thrust to slow it down and land safely. Actually, you do it a little differently. The way you come down is you come down in a glide, and then you kind of tilt the helicopter backwards. It has a lot of forward velocity at the end, and slow it down that way. Because if you just do it vertically, actually you'll pop up. And if you pop up, you'll be too high. Your blades will have zero velocity, and then you'll just sink down too fast. I told you the hardest maneuver is chaos. That also worked out. This is a sustained chaos. The helicopter is supposed to stay in place while rotating around all of its axes and ideally pirouetting as fast as possible. So maybe like 1 to 2 times per second the tail goes around while it's flipping and rolling. You can do this essentially a full tank of gas, which is about 8 minutes. It can sustain this maneuver, which means that, we couldn't experiment longer than that. Then for the last slide of the lecture, what I actually want to show is something slightly forward-looking that might be of interest to you guys. I know we're out of time, so if you want, you maybe can look at this offline, but I want to make sure you know this exists. So there's a slide just showing some current and future directions that I think are pretty exciting, and also some initial work that are, if you're interested in those directions, that we kind of natural papers to look at, and then from those papers look at papers that they cite and they get cited by to think more about these problems. So hierarchy and exploration fall into the faster learning category, where clearly humans don't think at everything at the lowest level of abstraction. You don't think about going to lecture in terms of footsteps or muscle contractions. You think of it in terms of lecture and learning something, hopefully, and then maybe doing something else after and so forth. Transfer learning, very important to scale up learning in RL or imitation learning, is that robots don't all have to learn every task on their own separately, but they can share what they learned across robots, across tasks. Safety during learning is a big challenge. When you learn, it's easy to break things if you're learning through RL, unless you're very careful about it. So that's a big thing to worry about. Bringing in unsupervised data is kind of, I think, the thing people have been saying for at least 10 years is the thing that's going to solve all our data collection problems, and it's still a challenge. So if you can fully resolve it, you'll have a major result that people have been trying for a long time. Grounded language. There's a few other papers on this too. NYU group / Facebook had a paper. DeepMind had a paper too. And they're all cited in here, so you can check them out from there. Imitation learning, I think Right now, reinforcement learning is very popular, but actually in practice, learning involves just as much imitation as reinforcement learning, most likely, and to get to very reliable, good systems with less need for kind of trial and error from the robot, imitation will probably play a big role. Another way to think of it is think of what you would be doing right now if all the other humans hadn't lived before us. Then you'd be much living like a caveman, and it'd be a very different life. And you would have the same quality of reinforcement learner, but you wouldn't have the same ability to learn from other people because the other people hadn't been there yet. And then a big one, as AI gets more powerful, is to think about value alignment of AI with humans and how to make sure things stay safe. Thank you. And I think we're out of time, but if you have more questions, I'm happy to hang around a little longer.
Great. So see you all on Wednesday for the